レット。はい、いただきます。Where the hell is my iPad? I can hear it from right here. Where is it? Oh, it's here. There it is. Couldn't find my fucking iPad.
ロマンがないね。 Oh, sorry, I didn't see the why did? What? Oh, no. Okay, so it did pop up. Um, yeah. Thanks for, you know. Yeah, although I just finished eating, so unfortunately we're almost done. Yeah, sorry, I was. Let me just hydrate myself. Right, yeah, we're done. I think, yeah. Yeah. I mean, I guess we have some strawberries, but I'm keeping that for dessert, so we're gonna actually start doing some work. Well, not work, but productive stuff. But yeah, K-Style, although, yeah. Has it been a while, or sorry, I'm trying to remember who you are, and I'm like, have I seen that? Sorry, has it just been a while? I do apologize. My memory is trash. Also, what emote is that? Twilly. Twilly. Sorry, I'm not really familiar who this is. Do you recommend them? Alright, so let's see, where is my I think I have it as PDF. Fix a phone. Oh, okay. Yes. Although those did get fixed. Or actually, I don't know which one it was at the time. Sorry, let me just open this first real quick. I can probably show it on screen. Give me a sec. Let's see. So we're gonna nothing problematic on screen. Need to move this iron out of my way. Okay. Boop. And I don't know. Maybe I was fixing this one, in which case, yeah, it's fixed. It's Oh, no, okay, it's powering on right now. I might have been fixing this one as well, which is totally dead as well. But the battery's no longer bulging for this one, so that's good. And then this one, I was able to flash it with the right ROM, so those were successful. I'll probably consolidate it into like a quick YouTube video. Not because it's interesting, but just more of like a log. Yeah. So, although having used both of them so far, I am feeling this a little bit more just because the screen is intact. So I might use this. I might daily drive this from now on. I'm just waiting for a case from Amazon to arrive, but then I'll probably daily drive that one, and then this Samsung, this Galaxy S7 Edge. Come on. Did it just turn on? Power button. Well, whatever. Figure that out later. I might use that as like, like a stream deck or something. So I was thinking I could use it as a stream deck. But we'll see. Okay. Anyway, so for today, what I actually need to do, though, is I need to finish reading this paper, which is Electrostatic Trapping of Ammonia Molecules. We have a journal club tomorrow, and admittedly, I'm not really done reading the paper. Although thankfully, so really the paper is this long. Alright, it's not fully on screen. Really, it's this long. This side is a different paper, and this side is a different paper. So it's not too long of a paper. It's just covered in terminology that I don't understand. Get a drink of water. But it's fine. I'm an undergrad. I'm not expected to significantly contribute to the discussion. Like, it'd be nice, obviously, right? But there's an acceptance that I don't, or that, they know that I won't necessarily have the requisite knowledge to participate in the discussion all that much. So they're not gonna be too mad that I can't really comment on anything. But anyway, so let's get started then. Or let's continue then. So let's see, where do we leave off? So they use deuterated ammonia in xenon, and they load that mixture into a vacuum. And let's see. Yeah, so we were talking about how like say with actually, now that I think about it, I'm not quite sure what. So an atom can have like SPD. I forgot what the orbitals are called. Can a molecule have like SP, whatever orbitals? Is that a thing? Or is it talking about like specific? Honestly, it's been so long since I took chemistry, I don't remember. Okay, so that's what I thought. So the S and P, like, that should be on a per atom basis, and then depending on what orbitals each atom has, it'll describe the total configuration of the molecule. So they're looking at, like, here, magnesium hydride. You can see how the magnesium has a 2s and a 3p orbital, and the 3p kind of interacting with the s orbitals of hydrogen produce this hybridization this sp hybridization that then explains the linear structure of magnesium hydride, right? So yeah, so anyway, so they were talking about how right, so our molecule is deuterated ammonia, so it's nitrogen and then deuterium, which is just hydrogen but with a proton like jammed into it, right? So yeah, so the hydrogens will have I guess 1s, is that right? It should have a 1s orbital. And then the nitrogen will have what orbital does? Oh, so I don't remember. I guess it has up to 2p. Okay. So then the 1s and the 2p orbitals or the 1s orbitals of the hydrogen and the 2p orbitals of the nitrogen should hybridize and give you sp or hybridization. And that is where, wait a sec. Yeah. So you have I guess a superposition of sp and then sp orbitals, and then depending on which one depending on which one you have or what the mixture is, if you put it in an electric field, then by the Stark effect the electrons will shift to one side of the field, but specifically relative to the molecule, s and p orbital or non-hybridized orbitals will have the electron shift to the left, while hybridized orbitals will just fundamentally be kind of right biased. So, or sorry, left in the sense that if the electric field is going left to right. Yeah. Yeah. Right. So we talked about that, and then we talked about how the reason why they use deuterium is because I guess the energy shifts that occur when you put the molecule in an electric field, or when you put the deuterated ammonia in an electric field, are reduced. So therefore, it's easier to model the behavior as linear, as opposed to if the shifts were large, or rather a large function of well, yeah, I said it before, right? Like if you take a curve, then well, you can't really model it as a line, but the more you zoom into a curve, the easier it is to model it as a line, right? So therefore, I feel like it makes sense that they chose deuterated ammonia. The energy shifts, or I guess they say the magnitude of the inversion splitting. So I'm not quite sure what they mean by what is inverting here, but the splitting is probably the splitting of energy levels, of degenerate energy levels. So they're saying that the magnitude is reduced. So it's kind of like saying, if we were taking a curve and we were just kind of zooming in on it, then at some point it's possible to approximate it as a line fairly accurately. So in the same way, if they just reduce the splitting a lot by using a deuterated ammonia as opposed to regular ammonia, then it kind of makes sense that it's easier to approximate their data as a line or as linear. Or it's easier to approximate the behavior as linear. Okay, so that was 2 paragraphs. Anyway, let's see. So the deuterated ammonia molecules pass through a 1 millimeter diameter skimmer into a second differentially pumped vacuum chamber, and fly into a short pulsed hexapole that acts as a positive lens for the selected deuterated ammonia molecules. Okay, so yes, immediately there's tons of words that I don't understand. So I'm not really sure what a differential pump is, so we'll keep that in mind tomorrow and during discussions because I don't know what, they have a diagram of the apparatus and I'm like, okay. And there's a hexapole, short pulsed hexapole, which I don't know what it is either. But then they say this acts as a positive lens for the selected deuterated ammonia molecules. After exiting the hexapole, which is, let me pull the diagram up on screen so I can see better. Here we go. So it's the thing on the left here. So the skimmer is this little cone thing, which I guess makes sense. I guess what's going on is that you have this kind of cone, or what do you call it, a funnel, but it's facing the thing that's spitting out these ammonia molecules. So only the ammonia molecules in the dead center will pass through the apparatus, and the rest kind of just deflect away because the funnel, or the inverted funnel, kind of pushes them away. And then when they say that's hexapole, it is literally a set of 6 poles positioned in a hexagon. Hexapole makes sense. Okay. I don't know what a pulsed hexapole is, but I guess this configuration acts as a positive lens. So a lens will focus. So is a positive lens just... Yes, it does focus? I don't know. Not quite sure. These are all question marks. After exiting the hexapole, the molecules enter a 35 centimeter long Stark decelerator. Okay. The decelerator consists of an array of 63 equidistant electric field stages. I guess those are those little humps there. When the state-selected deuterated ammonia molecules enter a region of high electric field, typically up to 100 kilovolts per centimeter, they will gain Stark energy. Okay. Sorry, and the state when they say state-selected deuterated ammonia molecules here, they discuss state selection earlier in the earlier paragraph. They're selecting what they call low field seeking states, but basically that means they're all they're saying is that they're targeting molecules that are in a state that gain Stark energy when the electric field that they're in is increased. Why that means low field seeking, my guess from yesterday was that it is to say that these are at higher energy in high electric field, so they're probably more stable at lower fields. So therefore, maybe they're low field seeking in that, you know, they want to be in a lower electric field. And again, to say that the Stark energy is need a breath. Okay. I just realized, is there a physics tag on Twitch? Whatever. Anyway. Yeah, okay. This gain in Stark energy, potential energy, is compensated by a loss in kinetic energy. If the electric field is greatly reduced before the molecules have left this region, they will not regain the lost... So when the state-selected deuterated ammonia molecules enter a region of high electric field, they will gain Stark energy. Okay. This gain in Stark energy, potential energy, is compensated by a loss in kinetic energy. If the electric field is greatly reduced before the molecules have left this region, they will not regain the kinetic energy. Okay, so the idea is, so the idea is you enter, or the molecule enters a region of a high electric field region, and it gains a lot of potential energy in exchange for losing a bunch of kinetic energy. And if you pulse it, is that what they're doing? They said electrostatic though, but okay, so, but if you can drop the electric field significantly before the molecule leaves this region, then they never regain that kinetic energy back. So Okay, so they say this process is repeated by letting the molecules pass through a series of electric field stages, which are switched synchronously with the arrival of the package of decelerating molecules in these stages. Molecule pass through a series of electric field stages, which are switched synchronously with the arrival of the package of decelerating molecules in these stages. This provides a method of decelerating sample neutral, maintaining initial phase space density as much as is done in charged particle accelerators. Okay. And autofocus does not work, does it? Okay. Something doesn't promptly delete. Okay, so I'm assuming I just have to look at it really quick. One sec, I almost have Discord open. Yeah, it's too cringe. Sorry, is this the is it the Yeah, no worries, I got it. You can delete it. Oh, wait, sorry. Are you facing? I guess you're facing the wall. Okay, yeah. Don't worry. I didn't see anything. I didn't hear anything. Yeah. Don't worry. Also, I see this. I guess this must be the iris cord. I see this other thing that you sent earlier. Yeah. Don't give me that kind of power. Yeah, just uninstall Photoshop. Just uninstall Photoshop. Well, I guess these days, like, Photopea is pretty robust, so I guess you don't even need to install Photoshop. Okay. Sorry. So, but yeah, no worries. I didn't see anything. I didn't see anything at all. Yeah. No matter what anyone says, I didn't see anything. Okay. Sorry. So, back to this though. I need to at least have read this before I can, or by tomorrow. So I had to do it. You know, I I'm not gonna say it's fine, right? But I can understand. Yeah, the temptation is I can understand the temptation, you know. I understand. Yeah. Although, you know, I've mentioned this before, but you know, I talking to my my colleague in the lab, right? We've talked before, and you know, we don't necessarily have the exact same opinions, right? So I'll say, like, you know, I can understand this, and he'll be like, no, I can't, and it's I don't, you know, we don't really, it's not a big deal, right? We're not actually arguing. It's just it's I've always looked at that, or that interactions happened a few times, and I've always thought of it as kind of a funny way in that we mean the same thing by saying the literal opposite things, right? Because in my mind, when I say I can understand, right, it's to, I've mentioned this, dozens, hundreds maybe of times already, but all I'm really saying is that given a sufficient amount of black boxing of, whatever I'm looking at, I can at least at some point understand the sequence of, things that need to occur or thoughts that need to occur in order to produce the outcome I'm observing. So when I say I understand, at least when I'm being very careful with my words, when I say I understand, I'm really only saying I can comprehend how there could be a series of events that lead to the outcome that I'm currently observing, right? And then when he said, or when he says I understand, or when he would say, he understands, or the way he uses the word understand, right, is very much in a more whether or not he validates the thing being observed, right? Which isn't something I'm making a commentary on typically when I say understand, right? So like I totally withhold the assessment for, later, or no, I don't withhold it all the time, but you know what I mean, right? So for the memes, exactly. Yeah. It's yeah. I mean, it's funny. Yeah. Well, I don't want to say, oh, is it funny? I don't know, but I can see the humor in it, right? I can understand the humor in it. Yeah. But no, it just kind of reminded me that yeah, because we're kind of saying the same thing. Like, I'll say understand, that doesn't mean I validate it, but he'll say I can't. And when he says he doesn't understand, he's saying he can comprehend it, but he doesn't validate it, which are basically the identical statement. It's just using completely different phrasing or completely opposite phrasing. So I don't know. That's always just kind of been kind of an interesting interaction that I've had recently. I mean, not recently, but yeah. Yeah, language is annoying, but but yeah. Anyway, yeah. Don't worry about it. I totally understand, man. It's you gotta do what you gotta do. Yeah. Oh, shit, sorry. What's I doing? Right. Sorry. So I do have to read this though. So I will continue to talk to myself. Yeah. So it does look like there is switching. So in what they call a Stark decelerator here, I guess there are electric fields that are turning on and off, and they're timed with when the molecules that you're loading into the decelerator are coming in. So molecule comes in, then like pulsing occurs, sort of, or the electric field is like on-off pulsed somehow. I don't know the mechanism, but and by doing so, you build the introduction of the field will convert the kinetic energy of the molecule into potential energy. But if you kill the field fast enough, the bare molecule will now just have potential energy but no kinetic energy, or very little kinetic energy, or less kinetic energy. And essentially what they're saying is that by doing that, like this on-off pulse of electric field on the molecule, if you do that multiple times, you can gradually slow down the molecule. And they say this method of decelerating a sample of neutral molecules while maintaining the initial phase space density, this provides a method of decelerating. Yeah, blah blah blah. So I don't really know what they mean by phase space density here. I'm a little. That stuff was a little confusing for me, so I will ask about that. But I'm not quite sure what they mean by why the phase space density is preserved. I think phase space density is short for phase space probability density. And I also understand that, at least to some sense, that phase space is a way of, I guess, describing, or is a way of, like, a phase space diagram is a way of depicting all the states of a system on one graph. So sometimes you'll see this as a 2D thing, but I've seen like 3D graphs which show, like, say what was it? like the interaction of like three molecules, and or you know the populations of, or actually not, I think the best one is like you'll have a active reaction going on, but there's three products that you can look at in that reaction, and it's kind of cyclic. And by changing various parameters, you can change to what degree like one molecule is being synthesized as opposed to others, and you can kind of it might be like thermally sensitive. So the phase space diagram for those three molecules would be a three-dimensional graph that kind of looks, and or a three-dimensional like surface, and any point on that surface describes the parameters that produce, you know, it describes the parameters and the molecule populations, again, for those given parameters. And then the totality of those would have been like a 3D surface. Of course, the more things you're looking at, the more dimensions you need. So I assume if you had four molecules, or if you had four, maybe you're looking at like a food pyramid or something, or something, right? Like, or not a food pyramid, like a populate, yeah, you know, like an animal population, like, you know, graph. If there's like four animals in the food chain, and you know they all interact to like balance out into like ideally an equilibrium, then you might need a four-dimensional graph. So maybe the three-dimensional surface changes over time, or maybe you add color to the three-dimensional surface to show the fourth, you know, axis or something, or whatever. But so phase space diagrams are kind of that, right? You use, it's a diagram that shows all the possible states of a system. I'm not quite sure what phase space density is, though. That's the annoying thing. I don't know what phase space density is. So we'll have to get some clarification on what they mean by preserving the initial phase space density. So, but they say this also happens in charged particle accelerators. Let's see. So then after this Stark decelerator, they have another pulsed hexapole. Okay. So they say a second pulsed hexapole at the end of the decelerator focuses the slow molecules exiting the decelerator into the electrostatic trap. Oh, we haven't even hit the trap yet. This was all just to slow down the molecule. Okay, that makes a little more sense. Okay. I was wondering, because they say electrostatic, that is, there's an unchanging electric field, and I'm like, you guys just pulsed the electric field, though. But no, that's not the trap. Okay. And sorry, this whole paper is about trapping ammonia, so, okay. So I don't know how these pulsed hexapoles work, but they automatically focus the small molecules exiting the decelerator into an electrostatic trap. Okay. The trap has a quadrupole geometry, and a cut through the center of the trap is shown in the upper part of figure 2. Figure 2 upper part. Okay. This is the electrostatic trap. On quadrupole. What is the quadrupole geometry? Okay, so they say quadrupole geometry, citation 19. What is citation 19? Okay, electrostatic trapping of neutral atomic particles is citation 19. APS. Ooh. I just want to see the paper. You know what? Fine. Can't see the paper, it's okay. Where was I? Okay. So maybe the quadrupole. Well, now they say this is a cutout. So, excuse me. So, what is the quadrupole geometry that they talk about? Well, let's keep reading then. So, restarting from the beginning. A second pulsed hexapole at the end of the decelerator focuses the slow molecules exiting the decelerator into the electrostatic trap. The trap has a quadrupole geometry, whatever that is, and a cut through the center of the trap is shown in the upper part of figure 2. Okay, and we see this, and I assume it's these hourglass-shaped things here. Okay. The 2mm diameter entrance and exit holes in the end caps enable the molecular beam to pass through the trap. Okay, so this is a hole that just goes through the trap. The inner radius of the ring electrode is... Where's my iPad ring? Yeah. Right, so okay, the inner ring radius of the ring excuse me. Okay. The inner radius of the ring electrode is 5mm. So I'm assuming so this must be like, yeah, it's like donut shaped. Okay. So this black thing that we're seeing on the top and bottom is probably the big ring, and they're saying that the inner radius of that is yeah, the inner radius of that must be 5mm then. Okay. And they say there are 2mm diameter holes in this electrode to allow probing of the density of deuterated ammonia molecules at the center of the trap via laser ionization detection scheme. Okay, we'll just have to pretend we, ignore that. Or pretend we know what that's talking about. Using the focused radiation of a pulsed laser at 302.4 nanometers, only the deuterated ammonia molecules in the selected state are multiphoton ionized. Oh, this is the laser ion. No, this is just describing the laser ionization detection scheme. Okay. Sorry, what happened? Are you going to change your stream from? Oh, yeah. No, thanks for the heads up. Keep forgetting that. Yeah. I mean, I guess that's one benefit of people that actually schedule their stream. I'll put the title of the paper in. So. Thanks for the heads up. Actually, not really bad. So, is there a physics tag? I guess not. I guess that's not surprising. I thought that maybe Twitch would have like a physics tag, but I guess not. Yeah. Okay. Cool. So I think that updated it. Thanks K-Style for the heads up. Let's see. Okay. Right. So this is, so I'm assuming that this area is just discussing the laser ionization detection scheme, whatever that is. Well, I mean, it seems pretty straightforward, right? So they're using a pulsed laser, and they pulse it at it, in such a way that only these low field seeking state molecules are multiphoton ionized, whatever that means. Yeah. So then, you know, based on how many ions you can get, you can determine the population, I guess. They say just before the probe laser is fired, the voltages on the entrance end cap as well as on the ring electrode are switched off. Okay. A constant voltage of negative 400 volts is applied to the exit end cap. The trap thus serves as the extraction region of a linear time of flight mass spectrometer. The deuterated ammonia ion signal is recorded using an ion detector placed further downstream. Okay. So, I mean, I guess that describes all the components inside this this diagram in figure 1. Okay. So, lastly is that if you blast it, I guess if you sorry, do photons have a charge? I know that's a really stupid question, but do photons have a charge? Interesting. It is, so it is massless and chargeless, which I guess makes sense because if it did have a charge, that would be kind of, I don't know, that doesn't sound very intuitive to me. But I'm just wondering because they say oh wait, no, this isn't a photon. It's ionizing. Yeah. Okay. Yeah, okay, so then I guess that makes sense. So the ammonia ionizes, or the deuterated ammonia ionizes, and then one of the and then I guess it's charged now, so then sorry, let me look up laser ionization detection. So, let's see. So I guess what I'm wondering is that does it just rip an electron off, and then you have just a positively charged ammonia molecule? Like, I don't know where the electron comes from. If I had to guess, it probably comes off of the nitrogen, but as opposed to the deuterium. So now let me read this carefully. Okay, so here we have multiphoton ionization, which is pretty straightforward, and it's as the name describes. It's when you need multiple photons to hit the molecule in order for it to ionize, or the amount of energy, imparted onto a molecule by one photon isn't enough to ionize it. So then you'd need multiple. That's all multiphoton ionization is. Yeah. Sorry, it's kind of cold. Let me go close the door. I was in the middle of charging my... Sorry, one sec. I was charging my bicycle, so... Let's close the door. It should be done by now. Grab a blanket too. Sorry. Oops. Okay. All right, back. So yeah, okay. Um, yeah, right. And this explains why they use, or looking at the Wikipedia page for um, laser ionization. Um, it discusses how, here it says, most organic molecules which are favorable for a photoionization method have ionization potential smaller than approximately 10 electron volts. Thus, APLI, which is what does it stand for? APLI is don't you hate it when they use acronyms without ever... I mean, I guess... Okay, so I guess APLI is atmospheric pressure laser ionization. But I wish they would explicitly define it at some point. But anyway, so they say, yeah, so thus APLI photon energy of about 5 electron volts, which corresponds to a wavelength of about 250 nanometers, which is in the ultraviolet part of the electromagnetic spectrum. So the reason why they're using 302 nanometer here is probably, again, because it must just, it must give a very good amount of energy. Or a photon, one photon must give some convenient amount of energy, or maybe that's the only laser they had. I'm willing to bet that part of the reason might be because that's the only laser they had at the time. That seems to happen a lot. But anyway, yeah. Okay, so it ionizes, and then you end up with I guess what they call a radical cation. Cool. So that makes sense. So this laser ionization will produce a a radical cation, as they're called. And that radical cation will naturally be positively charged. We called it a cation. I guess mainly the thing is with laser ionization, what I guess ends up happening is that you tear off one electron from your target. So naturally, if the stable molecule loses an electron, it's going to be positively charged. So it makes sense that that would be the case. You're not going to tear off a proton, obviously. That's in the nucleus. So naturally it'd be positively charged, and that's why they apply a negative 400 volt bias on the exit end cap, because now once you've laser ionized your molecule, then you can negatively bias the exit gate of the trap, and the molecule should just kind of be pulled in that direction. And then they say they have downstream, they have a ion detector, which would then, I guess, check. They say so. Extraction region of a linear time of flight mass spectrometer. A linear time of flight mass spectrometer. Not really sure what they mean by that. LCO, welcome back. How have you been? In order to transport the molecules into the quadrupole trap, some residual velocity is required. That makes sense, right? Like if the Stark decelerator totally stops the molecule, then you have no way of loading into a trap, especially since it's neutral. In the lower trace of Figure 3, the arrival time distribution of decelerated deuterated ammonia molecules at the center of the trap is shown relative to the time when the pulsed valve is open. Which valve is the pulsed valve? Oh, the pulsed valve is the thing at the beginning. Studying biology? Okay, so we're both studying sort of sciences then. No, man, I guess hang in there. You have my condolences. Biology was never never a strong suit for me, I think I mentioned. 75 is still really good though. I mean, as you say, it wasn't quite enough, I guess, but 75 is still a decent score, right? It's most of the way there. Yeah, I mean, excuse me. All I can really do is just try, right? Within reason, of course, but yeah, biology is actually. Let me tell you a funny story. I don't know if it's funny actually. It's just I kind of get a kick out of it. So back in high school, I did take one biology class, and I remember we were talking about animal hybrids and such, and the teacher, she wanted us to, I think it was she, pretty sure it's she. She wanted us to, it's supposed to be a fun class, and so basically the assignment was, just make an animal hybrid, make up one, draw it, and explain what characteristics are inherent and stuff. Or, I guess they said any organism, any hybrid organism. So, so me being the, super, environmentally friendly guy that I am, right, made a hybrid of a tree and a cloud. And I was like, yeah, man, this is a great idea. It's going to float in the air, and it's going to convert carbon dioxide to oxygen, and it's going to be all environmentally friendly. And I submitted it, right? Or I guess I didn't submit it, but, because it wasn't really an assignment. It was just kind of a little, here, have fun, kill some time. It's just kind of like a way to just get students engaged. But the professor at the end of the teacher at the end of the class was like, yeah, what what genetics does a cloud have? And I was like, dur. Yeah, I don't know. I was so focused on the good idea, I didn't consider that a cloud is not an organism. But anyway, yeah. After winter break, oh, do you get to retake the exam or something? Also, when is your winter break? Yeah. Yeah, one day I'll make a cloud tree hybrid and I'll show her, you know. Yeah. But anyway. Maybe at some point in the okay, well, I guess that's not too bad. It does suck because, ideally you don't have to, but I mean, now that you have the opportunity to retake it, I guess it means that, you can easily convert your borderline score into a solid score, right? I assume. Hopefully. Yeah. But anyway, yeah, sounds good. I'm just gonna keep reading this, annotating it. Yeah, don't mind me. Yeah, but wait, yeah, when is your winter break though? Is that soon or is it like way off? I mean, it's winter right now, right? So a week and a few days ago. Okay, so you're part of the way through it then. Okay. Yeah. Ends on oh, what? It's almost done? Well, that sucks. Yeah. I guess that's just how school is, right? Even in community, or I guess in community college, we had a longer winter break, but certainly in middle school and high school, we only had like a week or two. So, we had 2 weeks. I think we had a solid 2 weeks. But we also had Thanksgiving off, so around winter there were several holidays. So, yeah. Oh, okay, yeah, sounds good. You still got some time, but not a lot of time, obviously, right? So yeah. Don't let I guess you can. I'll let you study, and then I'll keep working on this as well. Yeah. But anyway, right. So if the Stark decelerator, in this case, so the thing so I guess what happens is, we send in pulses of deuterated ammonia. But even out of all the deuterated ammonia, we only want a specific type, which is this JKM quantum number 111 state. I don't know what exactly is the special thing about this quantum state, but we want that one specifically. And we select that state using what I guess this skimmer, as they call it, and well, so I guess the skimmer and this hexapole that they kind of have together, I guess, select the deuterated ammonia state that we want. And then it goes through the Stark decelerator, which really just is, they say, converts kinetic to potential energy. But the point is that it's slowing down as it goes through there, and I guess it's gaining potential energy, of course, but what they're talking about is that we can't totally stop the molecule in the Stark decelerator, or else it won't naturally flow into our atom trap, or in our molecule trap, in our ammonia trap. So they're talking about that residual velocity that you need here in this next paragraph. Yeah, kind of chill. Rain, Fall Guys, BG. I've never listened to the Fall Guys OST, or the soundtrack though. Actually, that's a good idea. Here, let me take a look. I've never listened to it. Naturally, because I've never played the freaking game, of course. But I wonder what it's like. Fall Guys. Fall Guys BGM. It's funny. I've watched a decent amount of Let's Plays of that game. I don't, but when asked, like, do I remember the BGM for it, I honestly don't. Okay, yeah, we'll take a listen. With one ear, of course, because otherwise I can't hear myself talk. Okay, it's getting a little noisy. This is fun. I'm listening. I guess this is the theme. Yeah, this is a fun song. Yeah. So, some residual velocities required in the lower trace of figure 3. Lower trace of figure 3. Where's figure 3? Lower trace. I guess it's this bottom one here. Okay. So, see, that's the good thing about printing the page, right? You can look at both pages at the same time. Okay, so the lower trace of figure 3, what did they say? The arrival time distribution, oh yeah, it's time in milliseconds versus the deuterated ammonia density, yeah. Okay, so the arrival time distribution of decelerated deuterated ammonia molecules at the center of the trap is shown relative to the time when the pulsed valve is opened. Huh? Sorry, wait, sorry, what? The arrival time distribution of decelerated deuterated ammonia molecules at the center of the trap. Oh, okay, I see. So what they're saying is that this is the distribution of how long it took for a deuterated ammonia molecule to enter the trap. So earliest it's coming in at like 4 milliseconds, and latest it's going off to like 12 milliseconds. But on average, most of the deuterated ammonia molecules are coming in at like 7 milliseconds or so. Okay. And that's timed based on when the pulsed valve, the thing that loads our deuterated ammonia into the system in the first place, is opened. So it's open pulsed valve, 7 milliseconds usually, it loads into the ammonia trap. Okay. It loads into the electrostatic trap. It's an ammonia trap. It is trapping ammonia, but specifically it's an electrostatic trap. Anyway, no voltages are applied to the entrance end cap and ring. And end cap is just referring to the trap, the top, or the opening of the trap. So there are no voltage applied to the end cap and the ring being something that's inside the trap. Let's see, the ring electrode. In this particular case, the Stark decelerator is set to decrease the kinetic energy of the deuterated ammonia molecules by about 0.9 inverse centimeters. It's 0.9 centimeters inverse. So what are the top units though? Whatever. So it's 0.9 over centimeters units. Let's see, per electric field stage. So every electric field stage, you get this 0.9 per centimeter like reduction, starting from an initial mean velocity of 260 meters per second. Meters per second period. Let's see. Okay, and then they said there were 63 stages, I think. Somewhere it talked about it's a 35 centimeter long Stark decelerator consisting of 63 equidistant electric field stages. Yeah. Whatever, so there's a reduction. This happens 63 times, I guess. It should be noted that only 1% of the deuterated ammonia molecules in the molecular beam are so let me get a drink of water. Yeah. It should be noted that only 1% of the deuterated ammonia molecules in the beam that are in the right quantum state. So it should be noted that only 1% of the deuterated ammonia molecules in the molecular beam that are in the right quantum state are also in the region of the phase space that is accepted by the Stark decelerator with these settings. So even out of, So out of all our deuterated ammonia molecules, there's only one state that we want. But even out of those, only 1% of that specific state that we want are in the phase space region that is compatible with our Stark decelerator. The mean velocity of the package of slow molecules arriving at the center of the trap at 7.7 milliseconds is 13 meters per second. So we were talking about how, I guess the 7.7 is where it's centered, but excuse me. Oh, actually, wait, no, the unit markings are here, so it's more like, yeah, so it's 7.7 for sure. Sorry, I'm just trying to think. You gotta go to the bathroom, but say about Soma. Sorry, Soma is what is that? Soma. Oh, same creators as Amnesia. Okay. Yeah, I mean, I guess take a flashlight. I mean, you have your phone, so that's a flashlight essentially, right? Yeah. Let's see. What's I doing? Alright, so let's see. The mean velocity of the package of slow molecules arriving at the center of the trap is 13 meters per second. Then I guess 13 meters is, what is it compared to initially? Okay, yeah. So it used to be 250 to 2,000 meters per second. But this configuration brings it down to more like 13. Yeah, so a lot slower. And has a relative narrow velocity spread of 2 meters per second at full width half maximum. This is actually a term that I've seen multiple times, like on data sheets. I'm not actually sure what it means, so let's look it up. Full width half maximum. Full width at half maximum. Let's see, so it says, in a distribution, full width at half maximum is the difference between two values of the independent variable at which the dependent variable is equal to half of its maximum value. So like, and the example on Wikipedia is that if you have a graph like this, and then you take the maximum value of the dependent variable and it's, or go to the halfway point and then you grab the width of it. So this width is full width half maximum. Okay. And what are they saying? So here. So for this, so I guess we're talking about so the mean velocity, or the velocity distribution, I guess, of these deuterated ammonia molecules has a center of 13. So if I were to draw this, and I'm assuming it's normal, but I guess that's not necessarily true. But so they're saying that they get 13 meters per second in the middle here, and then a spread of 2 meters per second at full width half maximum. So then, I don't know if the spread, let's look at the Wikipedia page again. Is the spread considered the total, is it like the from the middle or from the maximum to half maximum, or is it from one half max to the other half max? It's the width, I think it's the whole width. Whatever, I think it's 2 meters per second here. Okay. So, the latter corresponds to a translational temperature in the moving frame of the order of 2 millikelvin. Oh, how do you do this calculation? I don't know. We'll ask. Let's see. To load the trap, the voltages on the trap are applied asymmetrically as shown in figure 2. Oh, I see. Okay, here. So, I wish they would stop jumping back and forth between things. But okay, so figure 2 we have here. They're saying that to load the trap, the voltage are applied asymmetrically. Well, relative to where? Oh, sorry. This is what they mean. So the voltage on one side of the trap here, if we follow this graph, is -3, and the other side, almost the other side, a little bit before you reach the completely the other side is, oh wait, no, it's 0. Sorry, so I was looking at the wrong axis. So 3 millimeters from the center of the trap going from where we came from, the voltage is whatever corresponds to 0 inverse centimeters, I guess. Did they have voltage here? They say voltage is here, but they don't give us units of volts here. Or actually, no, it's here. Yeah, I was looking at the wrong diagram. They're here on the bottom. Okay. Yeah, and they are asymmetric. When you load the trap, it's at 10K, 12K, -400 volt, or -400. Then when you trap it, it's at 0, 12, -400. Okay. Interesting. Okay, well, okay, yeah, cool. So that it is asymmetric. Why is that? The deuterated ammonia molecules thus have to climb a last potential hill. Yes, they do. And are brought to a standstill near the center of the trap. The measured density of the deuterated ammonia molecules at the center of the trap as a function of time in this field geometry is shown in the middle trace of figure 3. Gotta shave. Or like my hands. Yeah, I mean, I don't know. Do you shave your arms? I mean, I think the thing I really got to do is I gotta cut my fingernails. Because my fingernails and my toenails have gotten kind of long. Yeah. Oh, the one thing I will say, I've gotten a lot more tan this year than last year. Like beard shaving. Oh, did that show up on screen somewhere? I mean, I do. That's like the truth, actually. Yeah. It's just so busy, you know. Beard or something? Okay. I mean, the truth is, I do need to shave my beard. It's been a it's been a while. Actually, it's sounded not showed. Okay, well, that's good. Um, yeah, no, I do need to shave. But it's just, I mean, you can tell, right? Like, it just takes too long. I mean, by the time I finish reading this today, it'll be, pretty late in the evening. So I'll just go straight to bed, and then tomorrow morning I don't have time. I have to go straight to work. Um, yeah. Pedro, welcome back. Got a savvy? Sorry, what? Savvy? Huh? What happened? Something happened, or? Let's see. Sorry, while I just try to get through this part. So the data shows reflection of slow molecules from the repulsive wall of the trap. At the center of the traps. What are they trying to say here? Mine like 8 months. I mean, I guess RN. Sorry, what is RN? What does that stand for? Sorry, the only RN I know is registered nurse. Sorry, but I don't think that's what you mean, right? Unless you do know a registered nurse, I mean, by all means. It's right now. Well, I mean, I don't really know if I have any advice to give you, but best of luck. Hey, Gurlin says RN. I'm like, the first thing I hear when I say RN is registered nurse, so, sorry, so the deuterated ammonia molecules thus have to climb a last potential fill on broad to stand still near the center of the trap. concave mirror of the trap. And how's this distinguished? Sorry. Sorry, I just, not just kind of leave your not to leave the conversation hanging there, but I'm just confused on what they're discussing here. Okay. Yeah. I don't know. I mean, maybe you're pre-med, you know, right? Excuse me. Okay, yeah, so I think I have my question here now. So we discuss here that with sufficient tuning of the Stark decelerator, the average time to arrive at the center of the trap. So I thought that meant that it just, they've tuned it such that it takes 7.7 milliseconds. Tiny. Yeah. Well, good luck with this person, I guess. Yeah. Let's see. Unfortunately, you can't give really much relationship advice. Maybe that's for the better, all things considered, right? Yeah. Also, sorry, I'm playing the Fall Guys playlist, and it's they're fun songs, but not really the mood that I'm in right now to study. So, yeah, maybe if I already knew the songs, it'd be easier to study with those on. But I don't know. Yeah. All right. So, what is this? So. Yeah, so I don't know what this is. I thought loading it into the middle of the trap had those on. But yeah, I had just a playlist going on, but it's a little bit too, I don't know. I think it's a little, I don't know. For me, it's a little hard to study on, but I don't think it's inherently because the songs are hard to study too. I think it's more because I've never heard the songs before. Like, if I already had heard these songs, like, let's say I played Fall Guys, like, if I had already heard the songs before, I assume I'd be so used to it that I could just, have it playing in the background and I wouldn't really notice it. But because I've never heard the songs before, it's just like new, like, auditory information just coming in my ear, right? So I think that's why it's a little distracting. Did you check Gmail? Oh, for this? Not really. Why? Let's see. GitHub, what is this? Oh, this playlist? What are these titles? Ohio. Ohio. Yeah, Ohio is it's just a government conspiracy, man. Oh, jeez. Did he make that, or is that someone else? Did someone else make that playlist? Let's see. So, yeah. So what is this? So yeah. So does. Yeah. So I guess, reaching center of trap does not equal loading. Maybe someone else's. Okay, well, it's still funny. Yeah. Let's see, so to actually trap the molecules, we switch the voltage on the entrance end cap to ground potential when the molecules have come to a near standstill inside the trap. Like, literally propaganda. Yeah, man. Ohio is just propaganda. Okay, yeah, so they switched it to 0. Okay. So then there's a high potential difference, or there's a high electric potential here, and then a low one on over here. Okay. I just don't quite get how that works, but okay. Let's see. So memes about Ohio. I don't know, man. I don't know what the deal with Ohio is. Okay, so the good. I don't know, man. I guess people just don't like Ohio. But we should get back to work though. I'm really just gonna skim the rest, but unless there's something worth noting. To actually trap the molecules, we switch the voltage. Yeah. We thereby create a near symmetric electric field configuration with a minimum at the geometrical center of the trap. I don't really... I mean, I guess I sort of see. So the center of the trap is positive 12,000 volts. And then as you go away from it, you've kind of got negative potential, or you're going down in electric potential. You go down to 0 going out of the, or going to the front of the trap, and then negative 400 going out the other side. But relative to 12,000, those are basically the same. So you do get a symmetric trap, or electric potential, like, what do you call it? Yeah. It is symmetric with the minimum being at the center. I'm not sure what's the minimum, actually, but whatever. The depth of the potential well in which the deuterated ammonium molecules are then confined is 0.24 inverse centimeters, giving a strict upper limit to the temperature of the sample of trapped molecules. This part I do understand, because otherwise they'd fall out of the well. Okay. Depending on the details of the trap loading, the actual temperature of the molecules in the trap might be as low as the translational temperature originally present in the moving frame of the decelerated molecular beam. Depending on the details of the trap loading, the actual temperature of the molecules in the trap might be as low as the translational temperature originally present in the moving... Okay, so what is this discussing? I don't know. The measured density of deuterated ammonia at the center of the trap as a function of time is shown in the upper trace of figure 3. The measured density as a function of time. At early times after switching on the trap, clear oscillations then density with a period of 0.5. I mean, I guess, okay, so I guess deuterated ammonia is slowly flowing into these traps, so then, going to the bathroom, call the police. I mean, I don't know what calling the police in the US is going to do for you, but yeah, go for it. I'm going to just try to keep going. The measured density of deuterated ammonia at the center of the trap as a function of time is shown in the upper trace of figure 3. And then we gotta drink of water first. Oh, excuse me. Oh, excuse me. Okay. So tired. Okay, anyway, back to work. Um, right. The measured density of a deuterated ammonia at the center of the trap as a function of time is shown in the upper trace of figure 3, yeah. At early times after switching on the trap, clear oscillations in the density with a period of 0.5 milliseconds are observed. These oscillations are a signature of the bouncing of the molecules in the three-dimensional potential well, when still only a relatively small region of space is occupied by the trapped molecules. The oscillations fade away after several milliseconds, and a steady signal from the trapped deuterated ammonia molecules remains. The actual signal observed from the trapped molecule amounts to few deuterated ammonia ions per laser pulse. As ionization of the trapped deuterated ammonia molecules only takes place in the focus of the laser beam, and the resulting ions have to be extracted through the 2 mm diameter hole in the exit end cap, the actual detection volume is less than 10 to the negative 5 centimeters cubed. This translates into a lower limit for the density of trapped state selected ammonia molecules of 10 to the 6th inverse centimeters. Not really sure what they mean by that. Okay, well, let's take a couple steps back. So, At early times after switching on the trap, clear oscillations in density with a period of 0.5 milliseconds are observed. Okay. So these are about 0.5 milliseconds. Okay. Right, okay. Okay. These oscillations are a signature of the balancing of the molecules in the three-dimensional potential well, when still only a relatively small region of space is occupied by the trapped molecules. Okay, so I guess it's like, there's a well, there's the molecular trap. And since there's only a few, like if you were to throw marbles into a, like if you were to throw marbles into a bowl, right? If you just had a big bowl and you just threw a marble into it, then it would slosh around at first if the bowl was empty. But if the bowl was full and you threw a marble into it, it's just gonna be like just to fall into it. Yeah. I don't know what I mean by the actual signal, though. So if trapped molecules amounts to few deuterated ammonia ions per laser pulse, as ionization of the trapped deuterated ammonia molecules only takes place in the focused laser beam, and the resulting ions have to be restricted to the actual detection volume. Okay, you're right. So inside the trap, there's a bunch of ionization going on, but okay. Come on, 11時やん。So, determine the trapping lifetime. The deuterated ammonia density at the center of the trap is monitored as a function of the time lapse since the loading of the trap. Okay. An exponential decay of the number of trapped molecules with a 1/e decay time is of 0.24 plus or minus 0.04 milliseconds is observed. Measured background pressure in the vacuum chamber is around 2 times 10 to the negative 8 millibar, I guess. Any collisions with background gas are therefore most probably responsible for the observed trap loss rate. Owing to the increased pressure in the chamber shortly after releasing the gas pressure, the trap loss rate is reduced slightly higher at early trapping times. Higher pressure in the chamber after releasing the gas pulse. Excuse me. The deceleration and trapping scheme presented here can be applied to a large variety of neutral molecules. For this, the molecule under study must have a sufficiently large positive Stark shift in experimentally feasible electric fields. Furthermore, a pulsed beam with sufficiently low initial kinetic energy is required. On the basis of the criteria, molecules such as hydroxy. And some other appear to be excellent candidates for heat trapping experiments. Especially the trap can be further cooled using evaporative cooling, using laser cooling on row vibrational transitions, which for study of cold molecular interactions, collective quantum effects in molecular systems, and physics of mutually interacting dipolar molecules. Okay, interesting. I'm glad it's feels like what we read before is kind of adding to us here, so that's good. I'm glad they selected this article because reasonably difficult read, but also reasonably short that it's feasible to read it in time. Thankfully, a very achievable read. So, looks like Elseo's not back, which perhaps is a little concerning, but I'll trust that he's alright. So anyone else that came by, thanks for coming by. Take care, stay safe, have a good evening, and I'll catch you guys later. I'm gonna sleep. I'm tired. お疲れ、おやすみ、終わり。